So today we're going to pick up where we left off. That's what we always do. Where we left off was starting to talk about dynamic allocation. In C, C++ is the same as C in everything we're going to talk about this week. And we left off contrasting this with Java. So the big difference between C, C++, and Java is the way that dynamically allocated things are reallocated. So there's two parts of allocation. There's malloc, or new, which creates an object, and then sometime later, when that object is no longer needed, there is in C called free. In C++ is a delete command. And Java doesn't have this. So what happens in Java is that there's an automatic process where memory is, objects are free when they're no longer accessible by any pointer in your program. And that's called garbage collection. It has some huge advantages, so that the problems that the problems that we're talking about today don't, the dangling pointer problem, it doesn't exist in Java. But C and C++ approach, this approach called explicit delete, has the advantage of gives the programmer direct control of the lifetime of a dynamically allocated object. So the way this works is that there's a region of memory called the heap. If I draw a picture of memory, I've done this a few times, like that's all of memory. There's a part of memory that contains all the things that are statically allocated. So this is all the code and all the little variables, and actually a few other things. Okay? And an easy way to think about this is just think about the heap is what comes next, and it sort of grows down as needed. And this is almost precisely the way it used to be in programs when you have a 32-bit address space. The address space is fairly limited, and so it was basically, actually the very beginning of memory is used, and then this stuff would be here, and keep it over below it. With the 64-bit address space, the address space, the possible range of addresses is huge, and so you could really put the heap anywhere, so long as it's distinct from the static allocated stuff. So the compiler controls the allocation here, and then it gets stopped at a certain point. And the rest of the memory is available for allocation during the runtime. And this happens in C and C++ by linking in a library. So the library implements these two methods, malloc and free. Malloc allocates something from the heap, free frees it, so that memory can be used. So the way this works is that this library is maintaining a data structure that records what part of the heap is currently allocated to something and what part of the heap is not. And when you say malloc, it goes through this data structure and finds a place that's big enough to store the n bytes you asked for that isn't already allocated. And this process actually turns out to be fairly complicated in order to avoid a problem called fragmentation. And when we just touch on this in the assignment for next week, you're going to see a little bit of this. You can build a simple allocator. And then when we come back to the stack, maybe next week, I can't remember now, or maybe after the break is gone. I think next week, no, after the break. We'll talk a little bit more about this feature of the heap. Allocation is a bit complex, but it really doesn't matter for us right now. And then when you say free, what it does, so when you say free, you provide a pointer. And it just goes to that location and marks all of the n bytes that are allocated to that location as being free. And the reason to do this is so that that memory could potentially be reused the next time you say malloc. Make sense? And if you write a program where you never do this or you don't do this at the right time, And this program has a bug called a memory leak. This is what we talked about last time. So the idea of a memory leak is that available memory leaks away because you're not freeing everything. You allocate a bunch of stuff, maybe you free some of it, but some part you didn't free. And that part will never be reused. And the program runs long enough, then the amount of memory that can then be reused grows, the program grows, and eventually it could grow so big that it will run slowly and eventually stop running.
I was just gonna ask, are we gonna touch on reality?
Yeah, so we'll see an example of reality. Maybe I can't remember now. Let's see Wednesday, Friday. But we're not going to read it. So there's some versions. We're going to look at reality specifically because it's one next feature that's going to go. It's when we do lists. So we after the query. And there's a couple other letters you can put in front of this. And you can see them all. If you just say man malloc, you'll see all of them. Malloc is sort of the basic, the lowest level one. That's all. All of them use malloc. Other questions?
About pointers, does
About
about
what?
spirit is, does the pointer spirit is after school?
Yes, that's what we're going to talk about. So if you do something like this, right, you allocate something and you free it and then you try to access it, that's another kind of bug. And that bug is called, well, this pointer, at this point it's called dangling pointer. And that's what we're going to talk about today. That's a very serious bug. It's a bug that doesn't exist in Java. And in fact, use that. Okay. So that's the main point of today. Here is, a description of free. The parameter to free is a pointer. The parameter malloc is the size. You get the pointer. Now you'll see from this is that the allocator actually knows when you give it a pointer, it knows if that pointer points to memory that's been allocated, and it knows how many bytes have been allocated. You don't tell it that. It doesn't, so when you call free f, it doesn't do anything with your, or p here. I'll change that. It doesn't do anything with the variable f. So if the variable f after this point, say it was the address 1000, it's still 1000. Calling free is just a procedure. In C and in C++, well, in C and in Java, all parameters are passed by value. So free can't possibly change the value of that. What it does is marks what f points to. If f points to something in memory, it marks this as available. So calling free marks is free. And the consequence of that is if you were to call malloc again after this, it might give you back that same point. So you shouldn't use this after you call free. And so it's a good idea. It's a good idea to do that. Is that equals 0 or equal capital N-U-L-L, which is the same as 0. Every time you call malloc, it's zeroed out. So if you do this, this is that. We'll talk about that using a dangling pointer. But if I do this, equals 0, or you can do this, null, same thing. And then I do this. That's also not great, but it's not a dangling pointer. So if you do this, this is dereferencing the null pointer. And that will cause a segmentation fault. And the reason for that is that at the very beginning of memory, the low addresses are reserved by the operating system. They'll never be used by any program. And any attempt to access this region of memory causes a hardware trap. So if that pointer value is 0, it's pointing up here. And if you try to read from here, the operating system will do the signal. And seg faults are great because you can figure out where the error is, and we're going to do that. But if you don't have this, and then this points here, that will just work. There'll be no error at this point. You're just writing into memory that you could have written into before, but now it's possible that that memory is being used by something else, and it introduces a bug. And that's why dangling pointers are really bad, because they don't, the symptom doesn't show up right here, it'll show up later. It's sort of a corruption of memory. And it's a really easy error to make.
You just said seg faults are great, but
Yeah.
seg faults can usually be caused by a number of different things. And
That,
You
well, yeah, so,
you also followed it up with, you said it's easy to now solve it because it's a seg fault.
I didn't say that, I said easy to figure out where it is, where it happened.
Okay.
I'll show you. Yes, so, anyone who's experienced a seg fault would think what I said was outrageously stupid. Which is why I said it, because they're bad, okay? But this is so much worse. Okay, okay, so, yeah. So I've got a couple programs that we'll look at here. So here's the first one. So this program, okay, so it allocates an int. And then p points to the int. And then it prints the value of p. And then it frees it. Okay, so at the line that where the print is, the first one, which one? Right after the free, p is a dangling pointer. That is a bug. But you'll see it's perfectly fine. It's going to print out the same pointer. So before and after the free, we'll have the same number. So we'll say p equals some number. That's where this object is in the heap. There's p pointing to it. And then we'll free it and we'll print it again. It hasn't changed, pointing to the same spot. And then I'll do the really bad thing that will often cause a really bad problem, which is star p equals 100. So now I'm using the dangling pointer and storing a 100 into memory that is no longer allocated. And then I'll print the pointer again and the value that it points to. And this is a serious, serious bug, and yet the program works perfectly. You have a question? So hang on, I'm going to run it. Okay, so that's where it happened to be allocated. After I freed it, so before the free, there's an int that's allocated there. And I can put things in it, it'll stay there, all's good. After calling free, and this print is after the free, there's still that location in memory. I can still put things in it, but it's no longer allocated. And then I put a 100 in, and you'll see the 100 is there. So at this point, there's actually no way to tell that there's a bug. Any test you run with this program, without adding extra code, the program works, but it has a very serious bug.
So what if after you freed it, you try to dereference p?
That's what I did.
No, you just printed the address.
No. So what if you dereference p?
So, no,
That's dereferencing p.
yeah, but you already said, no, I just mean that once you freed it, what is at the location of the dangling point?
Same thing that was there before.
Okay.
So,
Just override.
so the question is, when you allocate something in memory, what's there
No,
before you access it? Well, that's what you just asked. So what you said was, I'm just helping you understand what you asked. And if, and if we don't agree, then I don't know what we're gonna do. So, after the call to malloc, I've got to point to the points here. And now you're saying, well, what if I dereference that? So what's here? Well, it's not initialized. It could be anything. It'll actually turn out to be 0. So we can just put this, we'll move this print right here, right? Well, let's just do it there first, okay? And I'll comment out all the other prints so we know which one is printing. This is a great question, I'm glad you asked it. Especially if we agree that, right, it's 0. But why is it 0? It's 0 because that memory hasn't been used before. But it's not set to 0. It could be anything. This is an uninitialized object. Okay? It's like calling new in Java with a constructor that does nothing. Now in Java, if you attempt to access an uninitialized variable, you get an error usually. But you don't get that error in C. So the the other question, the question you really asked in this one was here. But it's the same. Nothing changes about the value of the memory just by reallocating it. Okay. And then the program that I wrote here gives it a value. And I could have given it a value anyway. I can move this up here before the 3. Same thing will happen. It's going to work. Okay? Because freeing doesn't change anything about the value that it points to, and it doesn't change anything about the pointer. It just goes into the data structure that free and malloc are using and marks that as being free. Okay? So now, I'm going to do this. I just have this code that I commented out. I'm now going to uncomment it. Oops. Okay, so you can all read that. Well, and also you can read the comments. Just look at the code. And discuss with each other what you think is going to happen now. Oops. I wanted to have this. You made me move this. All right, so let's look at the last line, the line that prints out the values of star P and star Q. What do you think it should print? 100, 200, right? Star P should be 100, star Q should be 200. That's not good. What happened? Let's go. 100, 100. Okay, so does anybody see what happened? What happened here? Yeah. Exactly. So what happened here was that the first malloc did this, allocated an int somewhere. And then I called free, and absolutely nothing changed, except that this now is marked as being available. So now I call malloc again for Q. And since this is available, the allocator decided to reuse that memory location. And interestingly, if you run this on Linux, you get the right answer. Because Linux is less, it just has a different allocator. It's less aggressive about reusing memory. And so it will pick a separate location for Q. If you pick a separate location for Q, you still have the bug. Eventually, it's going to cause a problem. But you won't see it right here. But this is what happened. This is running on Mac. It reused that location. Now, this is bad. Go ahead, red. This is bad. This pointer. We should never use that pointer again. So, there's the bug in this program really is the line star p equals 100. Because everything was great. I used star q to put a 200 here. Now, if I just stopped there, what would happen? So if I eliminate, I said this is the really bad line. So if I eliminate that and I run it, what's going to happen? What's going to print? What's the value of star p?
It should be
200, 200. Yeah. Okay. So there's another bad place, which is right there. There's 2 times I've used the dangling pointer. I should never use it. The second one is actually not quite as bad because here the bug sort of shows up in the place where the error occurred. Right, so the error is star p, I shouldn't dereference it. And I look at it and say, oh, star p printed the wrong thing. And so I could probably, maybe I can debug that. But when I have this thing here, star p equals 100, where does the bug show up? Well, it shows up down here with the wrong value of q. P's okay. And that's the key feature of this dangling pointer problem that makes it so hard to diagnose. Is that when the error occurs, you don't necessarily know what caused it. Right? This error was writing a 100 here using P that you never should have done, corrupting the value of Q. Does that make sense? So let's now just go back to the side. I have another example. So where this kind of error, this is yeah.
I have a question, because you're saying that you kind of knew the behavior based on the allocator of the operating system. So can this problem be avoided if we just know what allocator we're going back to the Linux allocator?
No, all I said was that the bug symptoms are non-deterministic and they're dependent on a lot of things, including the idiosyncrasies of the allocator implementation. But your program shouldn't rely on that. And in fact, the bug is still there, and you will still see this error in the Linux compilation of the program. You just won't see it right away. It does reuse that. I mean, you can solve this problem. You never have a dangling pointer if you never call free. Right? So the allocator could do that. You just ignore all calls to free. But then your program is in memory. So in order to avoid both bugs, that's the bug. So, and in this example, we're going to come back to this later, but here, the question that this slide asks points out why this is so hard. So this actually comes from the operating system implementation of message passing. So when you receive a message the operating system receives a message from the network, it creates a buffer to store it, and then this buffer moves around the operating system. And so the first procedure is a procedure called receive. It creates the buffer to store the new message in the just came in, and this is called an mBuf, message buffer, and it returns it to program procedure, let's say it's food, that then has in the variable MB, the first line of food, a pointer to this newly allocated thing. And it calls bar and passes bar as a pointer to this mBuf. And then it calls free, and it does the right thing here in setting MB to 0. Although in this case that's not necessary because that's the last line of this procedure, and that local variable MB will go away. So it can never become any pointer. And the question is that okay? Is it okay to call free there? So discuss that. Yeah, question? Yeah, that's a good question. He said, what does bar do? So let me ask you now, who thinks it's safe? Raise your hand. So I should just, if it's not safe to do it, I'll just comment that line out. I was trying to be smart. Okay, pretend I commented out. There is no call to free. Is that okay?
No.
Hands. Maybe. What if bar calls free? It's all good, right? I have this variable MD is pointing to something that was allocated. I pass the pointer to bar. Bar calls free. I don't have to say free it. It's been free. Okay? So maybe that's okay. But maybe it isn't. What if bar doesn't call free? What is that? That's a bug. It has a name. There are two possible names. Name the pointer or memory leak. Which one is it? Memory leak. Got it. So unless I call free here, maybe there's a memory leak. Now if I call free here, you all said it wasn't safe, or none of you said it was safe. Why isn't it safe? You're right. Why isn't it safe?
What if bar puts something in that after it frees, and then you're freeing it a second time, then you wouldn't be able?
Yeah, so if bar frees it, then we'll free twice. And actually, this is like SQL. I love that error, because free knows if it's free twice, and free will crash. So that's okay, but it's a bug, you're right. So that's one possibility, maybe bar free, I shouldn't have freed. But there's a worse problem.
What if bar changes the value of MB?
You mean what MD points to? Can't change MD, because that's just passed by value. So MD is locked, points to something. Maybe it's an and, maybe it writes some number there. That's not a bug, that's fine. You know, maybe it didn't want you to free it, but it's not actually a bug. It might save it, yeah. So what if bar has some like global variable x, and it says x equals MB, so global variable now points there. And then when I call free, that becomes a dangling pointer. Okay, so the key thing, we're gonna come back to this Wednesday-ish. The key thing to observe here is that you can't actually know whether it's safe to call free or not unless you know what bar does. And this is an example of some kind of thing we don't want to have in programs that you learned about in 210. Extra bonus points if somebody can name it. Yes, semantic coupling, exactly. So we don't want that. We don't want to have a kind of bug so that if somebody changes bar, then like an assumption somebody made about what bar does now breaks the program. So we'll come back to this. So this problem is generically very hard. What we're going to do is first look at some simple, I'm going to go through error again to show you a little bit more about it. And then we're gonna look at some best practices that you can use sometimes to avoid this problem. It won't actually solve this particular problem. We'll need to have another technique to solve that problem. That's the hard one. So let's just walk through what happens here. This is an illustration here where I have, the blue and the red stuff, that's the static stuff, the code, the global variables. And the green thing's the heap. Let's say the heap's all available, and I call malloc. And I say A equals malloc 16. So now I have a pointer A, so there's A, and it points to this chunk of memory. And I'm coloring the allocated parts of the heap dark and the unallocated parts light. Of course, that's not really the way it is. The heap is just a bunch of stuff. There's a little data structure on the side that's keeping track of what's allocated and what's not. Then I'll call malloc maybe a bunch of times. And this is just sort of what it looks like until you call it 3. So now I just called 3, and freed the third pointer. Right? So there's A, B, C, I freed C. And maybe I've freed B. So now I've freed 2 of these things. And now, when I call malloc, maybe it'll reuse that spot. So I have 1, 2, 3, 4, 5 pointers. 3 of them are great. This one, and this one. 2 are bad. And if I were to use one of those pointers, what I'm going to do is I'm going to write some value into the data structure that the purple pointer points to. And the purple pointer is perfectly innocent. It's like it's doing everything right. And yet, this bug in the orange code makes it so that purple code doesn't work. So you can imagine, because I know you all do this, is that you think of this as 2 modules, purple and orange. And you wrote purple and I wrote orange. And you have unit tests for purple. You don't do that, right? And you prove that your code, let's say it's, I don't know, it's a, what's the worst data structure you've done in 221 so far? Most horrible. What have we done? What is it? Oh, that's not so bad.
Yes.
Doubly linked list. Okay, so purple is a doubly linked list. And you have really great unit tests. Prove, without a doubt, that your code works. And then you combine it with my code. Maybe it's in a library.